Okay, in section 5 of module 6, we're going to look at some more properties of logarithms. So we kind of set up what a logarithm was last time. We kind of showed how we can change from exponential to log form to solve some equations. But the log has some really neat properties that's actually pretty helpful for us. So we have these different properties that we'll talk. The first three are the most important for sure, and then we'll look at some other less used but pretty valuable properties. So we have what's called the logarithm of a product. So this works both ways. So if I have the log of two numbers, so for example, let's say I have log of 2 times 3 of any base. I put base b on this, but this could be for any base. So I can write this as actually two separate logs added together. So log of 2 times 3 can be written as log of 2 plus the log of 3. So what this does is this takes one log and splits it into two, but of simpler things inside. The opposite is also true, where if I have two logs added together, say if I have log of 5 plus log of 2, I can write this as log of 5 times 2, which is log of 10. So I can take one log and split them up, or I can take two logs added together and put them into one single log. And we'll have examples of both. The second property we have is what's called a quotient, logarithm of a quotient. So very similar to the multiplication one, but you'll notice it is a subtraction here. So if I have the log of, say, 2/3, I can split this into two logs, which would be log of 2 minus log of 3. The opposite is also true. If I have log of 6 minus log of 4, then I can write this as log of 6 over 4. Just make sure the first one goes to the top, second one goes on the bottom. And I can still reduce the fraction in there like we always do. 6 over 4 we should know reduces to 3 over 2, so I can certainly write it as log 3 over 2. Our third, and probably for my money the most important property is what we call the logarithm of a power. So if we have the log of something to a power, and it could be a variable, it could be anything. Let's say I have log of 7 to the second power, whatever. Then what I can do with that power, that n out front that's a power, can be brought in front of the log expression. So I can take this 2 in my example here, and I can put it out front of the log. So I can rewrite this as 2 log 7. These are equivalent expressions. So I can take an exponent and I can put it out front. Or vice versa, if I have a number out front like 6 log 2, I can take that 6 and I can put it up top. So 6 log 2 can be written as log 2 to the 6. Some other kind of neat properties that, again, we don't use a lot in Algebra 2. You will probably use them more in future coursework. But you can see the log base b of 1 is always 0. So if you take the log of any base of 1, it's always 0. So, for example, if I take the log base 7 of 1, it's always 0. The second property says that the log base b of b is always 1. So if I take the log of 3 of 3, that would always give me 1. That one's a really easy one to prove because if I do log 3 of 3 in the calculator, it'd be log 3 divided by log 3. So those are absolutely the same thing, so that's going to cancel and just give me 1. Our last one would be log base b of b to the n is just equal to n. So if I have log of 4 to the 5, so I have these two 4s, a base of 4 and then a 4, the answer is just going to be 5. Alright, so let's look how we could kind of split up some of these logs and use some of those properties to not only split up but also put together. So if you look at the first one, we have log base 3 of 14. So I really don't have this multiplied or divided or anything, but what I can do is, what are two numbers that multiply to 14? Well, 2 and 7. So log of 14 is obviously the same as log base 3 of 2 times 7. So using our first property, which says that if you have two things multiplied, I can write that as two separate logs added together. So log base 3 of 14 is the same as log base 3 of 2 plus log base 3 of 7. The second one says I have log base 10 of pi over 4. So a really weird number, but if you notice, we have two numbers that are divided, pi and 4. So when two things are divided, we can write those as two separate logs. So it would be the log base 10 of pi, because that's the top, minus the log base 10 of 4. So I'm taking one log and I'm splitting it into two. Here on the next page, we'll actually do the opposite. We'll take many logs and put them together as one. So let's look at the next one. We have log base e. So we can write this, again, we have a top and a bottom. So I can split that up as a difference. So this is log base e of AC minus log base e of t to the 6. Now we can do a couple more things. Here you notice we have AC. Well, AC is a product, so now things that are products I can break apart as a sum of two logs. So this would be the log of A plus the log base e of c. So I've broken that down. Minus, now we have log base e of t to the 6. Well, now remember the last property that said if we have an exponent up here, I can bring it out front. So I can rewrite this as 6 log base e of t. So I've basically taken this one expression, which had lots of things, and broken them into more expressions that were basically a little simpler. Couple more examples. So we have ln. Now ln we've not talked about, but ln is a different type of logarithm. ln is what's called a natural logarithm. But if you ever see ln, it really means the same thing as log. It's just with a different base. So here I have x times square root of x squared plus 3, so these are multiplied. So I can break this down into two logs. Log x plus log of the square root x squared plus 3. So I was able to break that apart using our sum rule. If you ever have two things multiplied, and if you have x square root of something, those are multiplied, I can break those apart as a sum. Our last one here, we have log base 8 of 8x over 2x plus 1. These are divided, so I can obviously write these as a difference. So log base 8 of 8x minus log base 8 of 2x plus 1. Now 2x plus 1, although maybe it's tempting, there's nothing you can really do with that because it's not multiplied, it's added. There is no log property for addition, so that one would just stay just as it is. Now for the first one we can take it further because it's 8x, which is 8 times x. So I can actually write this as log base 8 of 8 plus log base 8 of x minus log base 8 of 2x plus 1. So now that we learned to break logs apart, let's try to put them together. So here we have 3 logs, and I'd like to write it as a single log. So I'd like my answer to just be one log that just says log of something. So The first thing I always look for when I'm putting them together, I look if there are numbers out front, which in this case there are 2. Any number out front of a log, remember, can be brought to the top. And the other problem, we took numbers that were exponents to the front. If the opposite's also true, if they're in the front, you can take them to the top. So this would be log base 2 of 4. So now we can put these two together because they're added together. So I can write that as log base 2. Now they're added, so that means I'd multiply the stuff inside. So those two become log base 2 of 4x to the 7th minus log 5 to the half. Well, now we have subtraction of 2 logs. So these 2 logs are subtracted, which means I can write them as a single log, log base 2, of just the quotient of the 2. So 4x to the 7th over 5 to the 1/2. So I took this original expression with all these different logs and I basically compacted it into just one. Let's look at another one. Now this one has some issues. Well, first of all, this is just a 6, right? So that's kind of an issue. So we have this 1/3 out front of this one, so I can take that up top first. So we'll have log base 5 of 8 minus log base 5 of 12 to the 1/3 power plus 6. So we were able to take the 1/3 up, so now I have 2 logs. Now these 2 logs can be put together because they're 2 logs with a subtraction sign. Subtraction of logs means the division of the stuff inside, so 8 over 12 to the 1/3. And then I still have this plus 6. Now I cannot really put the plus 6 with this log because it doesn't have the word log in front. So I can't multiply the 6 to there because there's no word log. So this would just be as far as you could go. Let's look at one more example. Here we have this ln, which again is our natural log. So I have this number 2/3, which I can take up top of this exponent, and that seems to be the only one. So I have ln of x minus 2 to the 2/3 plus 3 minus ln x squared minus 4. Now again, I've got a 3, which really can't be combined with anything, but these two, this log and this log, can be, because I can rearrange it. I could write as log x minus 2 to the 2/3 minus natural log of x squared minus 4 plus 3. So I can write that rearrangement. And now I can subtract these 2 logs by making them a quotient. So x minus 2 to the 2/3 divided by x squared minus 4. And then we just have the plus 3 on the end. Just remember, if you ever have a number and it doesn't have a log, there's nothing you can really do about it. So one of the main reasons we have these properties of logs is because we like to have these so we can use them to make equations and expressions simpler to use. So we can actually use these properties we just learned in conjunction with our stuff we learned in 6.4 to actually solve equations. So if you look here, we have log base 3 of x plus log base 3 of 2 equal 4. Well, we know that 2 logs added together can be written as 1 log, so log base 3 of 2x equals 4. So now we have a single log equal to a number. But if you recall from our change of form thing from section 4, if we have bx equal y, that is the same as log base b of y equal x. So if I rearrange this equation, the base of the log becomes the base of the exponential. So we have b becomes b. Whatever's on the other side of the log becomes the exponent, which in this case is 4, equals, whatever's inside the log, which is just y, which in this case is 2x. So I was able to take this equation, I have two logs, I put them together, and then changing forms, I was able to take it to something that has no logs. Now 3 to the 4th power is 81 equals 2x, so I can simply divide both sides by 2. So x would equal 81 halves. Let's look at one more. So in this case, we have log base 5 of x equal log base 5 of 7 equals negative 2. But we really have nothing on the correct side to combine. But what I can do is I can subtract that log base 5 of 7 to both sides, because if I'm going to put them together, I must have them on the same side for sure. So that'll make this log base 5 of x minus log base 5 of 7 equals negative 2. Now putting those two together, I get log base 5 of x over 7 equals negative 2. So now I can use my change of forms, which would make this x over 7 equals 5 to the minus 2. And again, that's because the base 5 goes to the power negative 2 equals the stuff in the log. Just changing forms as we've done. So now I can solve this lots of ways. 5 to the negative halves, if you remember, is 1 over 5 to the second. I can then just simply multiply both sides by 7. So x is going to equal 7 times 1, which is 7, over 5 squared, which is 25. All right. So just a couple ideas behind the properties of logs and how we can use them. Please let us know if you have any questions.